Hello, good afternoon. So I'm Andreas. Thank you for introducing us. This is Nikos. This is a joint work between Synelixis Solutions and Technical University of Crete. And it is based on a European-funded research project. So during the whole day, most of the talks focused on simulating a system. What we're going to talk about is how to simulate systems of systems. So the motivation behind our work was that when we're trying to build larger systems, we cannot ignore the network part. There are too many interactions, there are too complicated communications, and there are so many optimization opportunities that we cannot ignore either component. The problem is that the tools that are available, they either deal very well with one of the two, either the processing part, a processor system, memory, and accelerators and everything, or the network part, and trying to emulate anything that does the processing. And the other thing is that most of the simulators that are available, they are single-threaded. So that means that when you're trying to simulate extensively a very large system composed of very large amount of nodes, if you don't have concurrency, then the simulation will take forever. So what is exactly COSSIM? COSSIM is an open framework that can simulate parallel systems. I prefer the term systems of systems, and it is a single framework. It does not consist of different pieces of software that you have to manually tie together. There's a single notion of time, and there is an accurate accounting of the processing and network interactions. It has a graphical user interface that is Eclipse-based, and is based on an IP protocol, and therefore the simulation can be made distributed. It integrates also power tools, and at the moment it's open and free. We are going to release it in the next coming period. We hope that there will be commercial support by us, and there will also be add-on packages to provide extensions. The key concept behind designing such a framework was not to throw away all the work that has already been done. And the example from today's workshop is that so much work that's been done that we have to take advantage of it if we want to produce something that can be used by a lot of people, and this is what we want. And therefore, we need to use well-established processing and network simulators. And we need to be able to keep everything that has been written as part of the development effort for these simulators. Therefore, we adopt GEM5 to use as our main processing simulator, Omnet++ to simulate the framework, MacPad and other add-ons for estimating the power consumption. And what brings everything together is CERTI, which is an IEEE compliant high-level architecture implementation. In GEM5, currently, the network model that is used does support only two nodes that are connected through a simple wire. There is this virtual Etherlink that just simulates a wire that goes from one network interface card to the other. And the major restriction is that only two similar systems can be simulated, either the same ARM processors or the same x86 processors, similar, exact same configurations. And there's no way that you can have a more complex topology. So what we are trying to do is modify properly GEM5 and break this virtual wire and tap on the Ethernet interfaces send them properly through the HLA libraries, and connect them to a network simulator that will enable us to do whatever we want with the network part. By this process, we can have an arbitrary number of nodes connected with each other. We can have a sophisticated network topology, whatever we want. We can have routers, we can have switches, we can have multiple bridges, whatever we want. Now, by breaking the systems, each system is independent. Therefore, each system can be whatever we want. One can be an ARM processor, the other can be a big little configuration, the other can be an x86 processor, whatever system we want. And last but not least, by using the high-level architecture, the communication between each Gem 5, therefore each system, is IP-based, and therefore the whole simulation process is distributed. You can either have parallel execution in a multi-core machine, or you can distribute it in a number of machines wherever you want. Now, this requires some libraries to be implemented, but also restricts the use of Gem 5 to only full system simulation, because we need an operating system and the network interface card. But at the moment, we fully support x86 and ARM processors. We have not tested for other ISAs, but I believe that there is no reason not to have support for that. And we also have to build some more updated versions for the Linux kernels that we're running. On the network part, we use the Omnet++ network simulator, and it integrates some HLA components so that it can be connected with the Gem 5 system. The challenge is that the network stack of the Gem 5 system is the full Linux network stack, but the network simulator uses some more simplistic network stack. Therefore, they are not compatible. So if we are willing to use whatever has been developed as a network model in the Omnet++, there has to be a bridge between the two. And this is what we have done. And therefore, we support everything that Omnet++ supports. And that means that you can have any kind of topology and also a lot of different kind of networks. The real issue with all these things, which sound very okay, very ambitious, is that there are synchronization issues. Gem 5 is a single-threaded application, and therefore synchronization issues do not arise. It's very easy to have everything working. But when you have different Gem 5 instances which are totally independent, maybe running on different machines and simulating different systems, then you have a completely different notion of time spread around. But you cannot do that with a system that is networked, and therefore there has to be timestamps, there has to be interactions between the systems. Therefore, we solve these issues by using the HLA architecture, which is meant to be used for connecting simulators. And we use synchronization mechanisms for two different tiers. The first one is to have a proper synchronization between a Gem 5 instance and its representation in the network simulator. And the second one is to have an overall global synchronization between all different nodes. This is a little bit, I'm not sure why it doesn't show some things. Okay, so we have the Omnet network simulator, which has a representation for each one of the nodes. There's our HLA connection between every Gem 5 node and every node in the network simulator. And therefore, we have synchronization per node in order to properly exchange data packets between the two. And Then we have a global synchronization scheme so that all Gen 5 nodes can be synchronized and have a common notion of time. Now, what do we get from all these things? Gen 5 is orders of magnitude slower than Omnet. Therefore, using Omnet has a very small impact on the overall simulation time. This example shows four systems, or a number of systems, ranging from 2 to 16, either x86 or ARM, that are connected in a single network and are simulated. In the first one shows the scaling when we are in the same machine. We have a quad-core machine, and you can see that there is almost no overhead by going from 1 to 4 nodes. As we move in it, we connect another machine through a gigabit network, which is larger, and then the messages that have to be extended have an impact on the overall performance. For ARM-based systems, we can see that the impact is far smaller than x86. I think it's mostly reflected on the work that's been done regarding on the one and the other. Apparently, synchronization does introduce a performance hit, and there is also the talk about how do we retain accuracy. So as long as we permit a free running of the Gen 5 instances, and we perform less synchronization between the different nodes, then we lose on accuracy because maybe we cannot intercept certain interactions. The finer synchronization intervals we use, we can be more accurate, but there is definitely a hit on performance. This one shows for ARM-based Gen 5 instances, booting Linux OS, and what's the impact when we use different synchronization time intervals. This is more or less from us. I hope that maybe we have some questions or interest on what I have presented.